Hello and welcome to Chapter 13, the very last chapter. You've made it this far. Keep going. In this chapter, we're going to talk about how we can use statistics to help make a public health announcement. Epidemiology relies on different types of study designs. Three that we're going to talk about in this chapter are cohort studies, case control studies, and cross-sectional designs. Cohort designs follow a group that isn't sick and measure exposures that occur and observe the group to see who becomes sick over time. They measure different variables to check for different exposures of interest and follow the group to determine outcomes. In that sense, this design starts with if exposures occur and follows for outcomes occurring afterwards. The case control study design begins with those who are sick, who have the outcome, and it looks back to see what exposures they may have had in common, comparing it to a control group that is not sick and looks back for the same exposures in that group. A cross-sectional study design assesses exposure and outcome at the same time, for example, in a single survey. One of the reasons study design matters is that it determines what kind of data you end up collecting. If you do a cohort study, you can collect incidence data. Incidence data is the number of new cases that develop in a particular time frame. That is something you can collect with a cohort study because remember, in a cohort study, in the beginning of the study, your sample does not have the outcome you're ultimately looking for. Anybody that gets sick during your study would be an incidence case. The incidence rate is simply the number of new cases that develop over the population that's at risk at a given time. You multiply that by 100 to get a percentage. The only study design that gives you incidence data is a cohort study. From that, we can calculate a relative risk, which we're going to talk about a little bit later. You'll see a lot of references in this chapter to 2x2 tables. I always think 2x2 is a little misleading because it just covers the boxes that are labeled in here as A, B, C, and D, but you still have to total the columns and the rows. Those are important as well. When we talk about 2x2 tables, this is the kind of setup that we are talking about. When we do epidemiology work and we're looking at study designs and incidence and relative risk, we have two columns that are labeled disease and not disease, and two rows that are labeled exposed and not exposed. Then we plug in the numbers that fit into those rows appropriately. A person in your study who is sick and was exposed to the exposure of interest would go into box A. There's a total of 40 subjects in this particular example who are sick and exposed. Subjects who are not sick but were exposed to the exposure of interest would go into box B. In this example, we have a total of 7 subjects in box B. You will see if you follow the exposed row over that you have an A plus B, and that total is the number of exposed subjects, and that's 47 people in this example. If you go down to the next row and follow it, you will see C plus D is the total number of subjects not exposed. There were 158 who were not exposed in this example. You should also do your column totals. If you look at how many people have the disease, that would be adding up A in box C, which is 45 in this example. 45 people have the disease. If we want to add up the column for no disease, we add 7 and 153, boxes B and D, and get 160 people in this study did not have the disease. If we go over to the final bottom corner, we will find the total number in the study, or A plus B plus C plus D, which is 205 subjects. We're going to be using these tables through the rest of the chapter. Remember, incidence is the number of new cases. Incidence rate is the number of new cases over the population at risk at any given time. And cohort studies don't include anyone that already has the outcome of interest. Those diagnosed with the disease during the course of the study are the incidence cases. Therefore, those who are in boxes A and C are incidence cases in a cohort study. If we go back for a moment, you will see boxes A and C are the two boxes of those who have the disease. A is those who have the disease and were exposed. C is the box of those who have the disease and were not exposed. The incidence rate in the example we just looked at would be 40 plus 5. the total who have the disease, over 205, which is the total population at risk during the study. We would divide 45 by 205 and multiply it by 100, which gives us 21.95%. That tells you that about 22% of your sample population develops your outcome of interest while in your study. The incidence rate would then be 22%. The other thing we can do when we have incidence data is calculate relative risk. The relative risk is simply the incidence rate in the exposed group divided by the incidence rate in the unexposed group. This is also sometimes called the risk ratio. Let's look at an example. If we use the same 2 by 2 table from before and take the incidence rate in the exposed group, box A, because remember we're only looking at the exposed group, so it's the subjects that got sick in the exposed group, over the total exposed, which is 47, our numerator, the incidence of the exposed group, is 40 over 47. Now we need the incidence in the unexposed group, so that's the subjects that weren't exposed that got sick, which is 5, divided by the total that weren't exposed, which is 158. If we divide our incidence rate in the exposed group, our numerator, by the incidence rate in the unexposed group, we will get 28.3, which is our relative risk. But what does that mean? If your p-value is significant, remember the p has to be less than alpha, otherwise it's not a significant finding. Then a relative risk of 28 means the exposed group is 28 times as likely to get sick as the unexposed group. Because you have incidence data, you can also say the exposure occurred before the disease. In other words, if a person is exposed to this risk factor, he or she is 28 more times more likely to develop the outcome of interest or the disease. This exposure would be considered a risk factor for this disease, and the incidence data would help establish a stronger link to causality. If you look at the little table on the right, it's also going to explain this same idea. A relative risk greater than 1 means the risk is increased for those that are exposed to develop the disease. A relative risk of less than 1 means the exposure decreases the risk of developing the disease. You would see a relative risk less than 1 for something like vaccinations as your exposure. A relative risk equal to 1 means the chance of becoming sick is the same in the exposed group and the unexposed group, which also means there's no association between the risk factor and the disease. By definition, that tells you your p-value is insignificant. Attack rates are also used in public health work quite a bit, and they are frequently used to determine the likely source of an epidemic or outbreak. The attack rate is simply the incidence in the exposed group over all of those exposed to the particular agent. That's in bold and italics because that's the place that people make mistakes with attack rates. You multiply the whole thing by 100 if you want to make it a percentage. You always want to start when you're determining your attack rate with your denominator. Those that are exposed to the particular agent goes in the denominator. If they weren't exposed to that agent, they aren't in the attack rate for that calculation. If 4 people got sick after eating their sandwich and 8 people ate sandwiches, you would have the 8 that were exposed to the sandwiches in the denominator and the 4 of them, the one that got sick, in your numerator. So your attack rate would be 4 out of 8. Even if you had 10 people that came to the lunch but only 8 of them ate sandwiches, your attack rate denominator is not the 10 that came, it's only the 8 that ate the sandwiches. So I tell my students in class, start with the denominator, with those who were exposed. That's your denominator in the attack rate. Then look to see, out of those who were exposed to the thing you're checking the attack rate for, how many of them got sick. If you want an attack rate for sandwiches, you start with how many people ate the sandwiches in your denominator, and then you go to your numerator, which is how many of those people that ate the sandwiches got sick. Remember, if there's 2 people that didn't eat sandwiches and got sick, they don't belong in your numerator. Next, you have your attack rate for punch. So you start with how many people drank punch. Maybe 6 of the 10 people had punch, and it turns out 2 of them got sick. So the attack rate would be 2 out of 6, or 33%. The key with attack rates is to make sure you get the correct denominator. This seems very simple. However, I have found that that tends to be an area where a lot of students struggle when they go to apply the actual concept. But what if we don't have a cohort study? I know you're all asking that question right now. What if you have a case control study? A case control study starts with a group that's sick and looks back to see what they were exposed to. With a case control study, we don't have incidence data and we cannot calculate a relative risk. We use instead an approximation of the relative risk, which is an odds ratio. You will once again set up a 2 by 2 table, but this time, because of the study design, it's only prevalence data in the table. An odds ratio is equal to the odds that a case was exposed over the odds that a control was exposed. It is important to notice a difference here. Odds are not the same as probability. Odds are the chances of something happening divided by the chance that it doesn't. For example, the chance of a baby being male is 50%. The chance of a baby being not male is 50%. The odds are actually 50 over 50, which is 1, which means the chance that the baby will be male is the same as the chance that the baby will be female. Let's look at an example. We're going to use a case control study. You'll notice we labeled the 2 by 2 table slightly differently. In this situation, our columns are going to be labeled as cases, those who are sick, and as controls, our subjects who are not sick. We still have exposed and not exposed for our rows. When we do this, we're still going to have number 4 in the A box, number 2 in box B, number 1 in C box, and number 15 in the D box. I should have labeled those, but I forgot to do that. You calculate an odds ratio by taking the group of cases that were exposed, 4, divided by the cases that weren't exposed, which is 1. The odds of exposure are going to be 4 to 1 in the cases. That's our numerator. We're going to put that over our denominator. Our denominator is B divided by D, which is the odds of the controls being exposed, or 2 over 15. If you divide it out, it gives you 30. I like to do it that way because I hate to memorize things, but if it's easier for you, the equation here simplifies to A times D, 4 times 15, divided by B times C, which is 2 times 1. And if you do it that way, you'll still get 30 as your odds ratio. We interpret the odds ratio fairly similarly to the relative risk. The relative risk is the chance of becoming sick, but the odds ratio is the chance of being sick. The other thing I want to tie in here is the last chapter, and we talked about using odds ratios and logistic regression. Remember, we use logistic regression when we have binary outcomes like alive or dead or yes or no. One of the reasons statisticians like logistic regression is that we can convert the beta values in the prediction equation to odds ratios fairly easily. If you look at your SPSS output from one of your regression equations and you look at the EXP capital B column, that's actually the odds ratio associated with the exposure and the outcome of interest when you hold all the other exposures constant. That's a helpful thing to be able to generate quickly in a computer program. What does an odds ratio of 30 mean? As long as your p-value is significant, it means the odds of a sick person having been exposed is 30 times higher than the odds of a well person having been exposed. The odds ratio can be used to approximate the relative risk when we don't have incidence data. It estimates that if a person has the exposure of interest, he or she would be approximately 30 times more likely to get the disease. However, since you're not using incidence data, you cannot be certain that the disease did not occur before the exposure. Your argument for causation is really quite weak. For example, you might find that those with less fiber intake are 30 times more likely to develop GI cancers. However, if it turns out that having GI cancer actually causes people to ingest less fiber because it upsets their stomach, it might be the exposure you are looking for actually came after the disease. You cannot say these things are causally related in any kind of temporal relationship when you're dealing with prevalence data rather than incidence data. Anytime you're given a relative risk or an odds ratio, you're almost always given the confidence limits. The researcher found the relative risk in the sample, and that means the researcher is then 95% certain if it's a 95% confidence interval, that the relative risk in the population falls in the parameters of this confidence limit. For example, a relative risk of 28 might be found in the study, and the 95% confidence limit might be between 24 and 29.2. That means the researcher is 95% certain that in the population the relative risk falls between 24 and 29.2. You will notice anywhere in that range, in that confidence interval, there's a positive relative risk greater than 1, which means there is a significant result. If you can't find the p-value, what you look for instead are the confidence limits. If the confidence limits don't include 1, it's significant. If the whole confidence limit is above 1, it's a significant risk factor. If the whole confidence limit is below 1, it's a significant protective exposure. But if 1 is included anywhere in the confidence limit, you don't have a significant finding. A relative risk of 1 means there's no association between the risk factor and the disease. That, by definition, is the null hypothesis. If the null hypothesis is possible in the confidence limits, that means you have an insignificant p-value. If the 95% confidence limits in your relative risk are 24 to 29.2, you have a significant risk factor in the exposure you're studying. If your relative risk confidence limits are 0.6 to 0.9, then you have a significant protective factor because the entire confidence limit is below 1. But if the 95% confidence limits are 0.9 to 2.7, you'll notice it goes over the value of 1. Because it bridges the value of 1, the bottom of the confidence limit is below 1 and the top is above 1. 1 is in that confidence limit. 1 is in the confidence limit, which means you have a possibility of no relationship, which tells you there is not a significant p-value. What you're really saying, or what the researcher's really saying, is that he or she is 95% certain that the exposure is either a risk factor, a protective exposure, or not related at all to the disease. So basically, the researcher is not sure of anything. Another concept I want to go through quickly is attributable risk. The attributable risk in the exposed group is the amount of disease or outcome in the exposed group that is due to a particular exposure. The way we calculate it is pretty simple. It's the incidence in the exposed group minus the incidence in the unexposed group. If the attributable risk for lung cancer among smokers is 0.89 or 89%, it means that 89% of the risk of lung cancer for smokers is from smoking. That also means that 11% is from something else. These are the types of headlines that appear in newspapers because people can understand them. You'll see these terms used a lot when you're talking in public health. Perhaps a headline of 89% of lung cancer from smokers is from smoking, or your risk of getting sick with the flu is 44 times higher if you don't get a flu shot. These are statements that most of the public can understand pretty easily, so they're used frequently. That wraps up Chapter 13 and the whole book. Congratulations, you've made it through. I wish you all great luck on your final. You're doing well. Take care and keep using statistics.